Hello, everybody.
Hello.
Hello. Okay, please put away your laptops. Okay, quick thing about the exam. So ultimately, I think it went very well. A lot of students seemed to do very well. It was 90 points in total. Nobody got a perfect score, but several people got really close. 2 people got 88 out of 90. That's certainly a very good sign. Overall, the distribution is extremely smooth, so pretty much every single point assignment you could imagine up to some level you get.
Can we see the PDF and not the CDF?
No, I don't have it. No, sorry, this is the, yeah, this is just the sorted, this is not even the CDF though. There's just, so every bar here is one student, I just sorted you guys.
Oh, okay.
That's what that is. So this here is the top 2 students have 88, and then basically got sorted number of points. So ultimately, if you're between 60 and 88, you're doing, you know, I'm not worried about you. Down here, these are very concerning. I just want to remind everybody today is drop dead deadline. I mean, I'm just being honest here. And I'm also worried if you have below 50 points. I think 50 points and lower. I mean, you know, this region here, it's very low. Right? Consider this as like the exam. If your final exam is not much different, that's 50% of your grade. So I am concerned in that case. If you decide to stay in the class, please come to office hours and we can chat and see how maybe debug what went wrong here. I mean, clearly other people have had, you know, less problems on this exam. So, you know, try to figure out what went wrong if you are in this, you know, in this region here, right? Certainly below 45, it doesn't look very good. Any questions about the exam? Oh, they're online. They're on Piazza, yeah. The solutions are online.
I have a question.
So for those, some people took it late, and so the TAs did a heroic effort of trying to get basically as many graded as possible before the drop deadline. I did not ask them to do this, but they actually did this, you know, because they thought it was important to you guys. So they basically came in Saturday and Sunday and basically graded pretty much the whole time to get everything done on time. So unfortunately, the late exams are not graded yet, but the solutions are online, so maybe take a look and estimate how well you did, in case you want to know. Yeah?
This isn't about the midterm, but on the course website, it says that homework 4 is due on the day before spring break. Is that
homework 5? That sounds accurate. Oh, say homework 4. Oh. I think that's incorrect.
okay?
That's the one that just, wait, homework 4 is the one that just came out?
Yeah.
It hasn't been posted on CMS or Piazza or anything yet.
Oh, I see. Yeah, no, that's a mistake. So the project is due the day before midterm. Oh, the day, yeah. Sorry, the day before. What is it called? Spring break, yeah. Okay. If you can, maybe post something on Piazza that it gets classified. Any other questions? Okay, awesome. So overall, actually, yeah, you did pretty well. And I'm actually very impressed with the first question. So I think the median score was 100% of the first question. So that's very, very impressive. Over half the class got every single question right. All right. What actually got people was the naive Bayes. For some reason, apparently naive Bayes was the hardest one. which I wouldn't have predicted, to be honest. Okay, so we're still talking about the bias variance trade-off. And so last time, or 2 lectures ago, I showed you that you can take the error if you minimize the square loss, but it generally holds more or less, and decompose into 3 very interpretable terms. The first one is the variance, second one is the bias of your classifier, and the third one is the noise that's inherent in the data set. And then we looked at these curves, and the curves kind of looked a little like this. Last one we looked at was early stopping, where we said just 2 things. Either you can do regularization, where you increase your lambda, or you can change the number of iterations that you optimize for. And if you start with an old 0 vector, then that's actually a pretty good way of regularization as well. And so what you get here is that basically as you iterate more, the training error goes down. And the test error goes down, then goes up again. And so this here is again the sweet spot. And so what's happening is here, basically the test error is too high, and we call this underfitting. So we're not fitting the data set well enough yet. We have more weight improvement. And here we are overfitting. So overfitting means we are learning too much about the training data, but it doesn't generalize to the test data anymore. So those are the 2 regimes. Turns out in practice, there's these 2 things that are very similar. So one is basically change the lambda, the weight in front of the regularizer. The other one is to change the number of iterations for which you optimize. Typically, there's one advantage that you have when you do this. When you change the number of iterations. And it turns out it's a lot faster in practice. Can anyone tell me why it's a lot faster to find the sweet spot when you change the number of iterations, rather than trying out many different values of lambda? Any idea? So actually, maybe let me just remind you of what I'm talking about. So you're minimizing, you have this weight vector W. That's in the 2-dimensional case, this would be the first dimension, this is the second dimension. You start with 0, and you have this loss function that you minimize, and loss function looks something like this. Here's the minimum. So as you optimize, you kind of move along this path to get here. And early stopping basically says, well, I don't go all the way there, I just stop somewhere early. And regularization says, if you do L2 regularization, then it says, I'm staying within a ball of some radius. And that's dictated by this lambda. So, and so basically, once you hit the ball, you basically, you make no more progress. You stick here, right? You stay here. And if you do L1 regularization, this ball just turns into, a diamond, right? So that's the slightly different shapes. So if you want to find the sweet spot, one option is to basically, we talked about cross-validation. So what we said is you take your trained data set and you split your trained data set into k parts, right? Or one thing you can just do, you can in the original, if you just do 1/4, then you just have training and validation. If you do k-cross validation, then you do this k times. And you train your data, your classifier here, and you evaluate it here. Okay, and that's basically how you can get a peek at the test error. The validation error is an approximation of the test error, right? So in some sense, you can basically look and you get these kind of plots. All you have observed is a training error, but when you evaluate your classifier on the validation data set, then you can look at what the testing error is, an approximation of the testing error. And then you do this for many different values of lambda. So, and you pick the one that actually has the lowest error on the validation set. Now, it turns out that's a lot faster if you do this method. Can anyone tell me why? Yeah? That's right, that's right. That's exactly right. Whereas here you don't have to do this, right? So when you try to find the right value of lambda, what you have to do is you basically retrain your classifier over and over again, and then once it's trained, it's converged, you look at the validation error and you say, okay, for this value of lambda, this was my validation error, and you try out 10 different values, and then you pick the best one. when you do early stopping, here's what you do. You just optimize, and you just optimize once. And every couple of iterations, you estimate the validation error. And you just keep a track, right? You just basically you save the weights in some file and say, this was the validation error. And then you keep optimizing all the way until the end. And then you look into your files and say, which one was the one that has the lowest validation error? It was this one here. So that's the one I'm picking. Okay? So in one sweep, basically, you get all these different values of n. Okay, so it's very, very fast. And so that's with expensive models like neural networks, this is what people do. Right? So you just train your neural network once for a couple thousand iterations, and then at the end you say, okay, well after 700 maybe that was the best, best model. After that I started overfitting, so you use that as your final answer. Any questions about this? Sorry? Well, it doesn't work for all methods, right? So not all methods actually have an optimization like this. So for example, SVM, you may just call a solver, like a quadratic programming solver. Then there isn't really a notion of early stopping in that sense. Yeah, so it's basically not always applicable. Any other questions? Yeah? How do you set your M? Well, you do exactly this, right? You basically, you train your classifier, and every couple of iterations, you evaluate the classifier you have right now on the validation set, and you keep note of what the error is. And that's basically this curve here, right? This is the approximation. The validation error is going to look very similar to this. And then you basically evaluate this over and over again, and you say, after you're done, you go back and say, that was the best one. And so you save the weights, you save the parameters at this time, and that's what you return. Does that make sense? How does it save time? Because for every single value, you do them all in one step, right? You basically just go through it, and you keep iterating. If you try different values of lambda, you have to, for every value of lambda, you have to do the whole optimization until convergence. Right, so the other plot is this. If you basically say, what's my value of lambda? Right? If my lambda is very, very large, my training error is the other way around. Right? So my training error goes up. Wait, how does it go? Sorry, it goes this way, right? This way and this way. Is that correct? So, so here actually try all the different values of lambda, but for every single value you actually have to do the whole optimization. Whereas here you just do the optimization once and you get all the different values for free. That's the difference. Okay, any more questions? Yeah?
How do we know the test error is all smooth and, it's continuous?
How do you know it looks exactly like this? And the answer is, I'm lying. It doesn't. In reality, it looks like this, right? In principle, it looks like this. So, I mean, it won't be that smooth, but it's pretty smooth.
You get pretty close.
Yeah, I mean, you have noise, right? You always have noise, so. Okay, any more questions? All right, so what I want to do next is kind of say, put you in the shoes of a data scientist. And imagine your boss tells you, train a new system, right? So for example, to do spam detection or to predict the stock market or, I don't know, whatever you want to do, right? So choose your industry. And your boss gives you a lot of data, and then she says, like, here's, you have to train a model, and the test error should be less than 1%. And so you train your model, and your error is higher than 1%. Right? So what do you do? And so that's called machine learning debugging. And so basically what you need to find out in this case is if your error is too high, we've now learned one thing, right? You have to know which part of the error is too high. Right? So your error consists of 3 different parts that are added up. Right? So this is your overall error. It's going to be variance, bias, and noise or something. Right? And so if you know which one is the largest one, then you know what to do in order to reduce the overall error. Right? And it can be very lopsided. Right? It could be something that you have massive variance problem, you have hardly any bias at all, and you don't have much noise. Right? So in this case, if you try to reduce the bias, you won't have any luck. Right? Or you try to clean the data and spend a lot of money to reduce the noise by half, right? Well, it won't help you much because you actually have a variance problem. Right? So you have to address the right aspect of your problem. So the question is, how can we debug this? And so what I'm telling you now is a very, very simple trick that you can use in practice, and I hope you will. And so here's what you do. You make a plot. And this here is the number of training instances you use. So you basically take your training data and you just randomly reduce it into subsample data. And so this here is basically using my entire training data set, and this here is only using a small fraction of it. And so basically what you do is you train your algorithm many times. So first you just train it on 1% of the data, very little, and then 2% and 4%, and so on. And you slowly crank it all the way up, training it in the full model. And what you want to see is how things change as you increase your data. And so this here is error. And let's say your boss dictated you here. This is the error rate that your boss tells you. If you get that much error, then we be able to ship it. And you get your bonus, and you move on, and you get a promotion, etc. You may even get a cubicle near the window. It's very rare. And so basically, you have to move your test error below this, right? And by test error, essentially, I mean, in this case, validation error. So what happens, right? So first, let us plot the training error. So the training error, when you have hardly any training instance at all, you just have one training instance, what's your training error? With any respectable algorithm who can still look at itself in the mirror. I just give you one training example. What's going to be the training error? 0, right? So it's going to memorize that one example, you hope, right? Otherwise, you may have a bias problem. And so as you increase your training data, what happens is the training error will only go up, right? Because your problem is only getting harder. The more data you have to basically be consistent with, the harder your problem. So you basically, as at the beginning, your training error is very, very low, and then you keep going. And so here, this is kind of what happens. Right? And what happens with the test error? Well, the test error, if you just have one training sample, is going to be horrible, right? Because probably most of the world will not look like that one example you downsample. So at this stage, your error is really, really high. And then the test error goes down, goes down, goes down, goes down. And the important thing is the test error is never lower than the training error. So the training error is a lower bound of the test error. So this is what your figure looks like. Right? And depending on how much data you have, you will either stop here, because now you've reached the maximum of your data set, or you stop here if you have a lot more data. Okay? All right. So let me just write this down. This is training error. And this is testing error. And so I claim there's two regimes in which you could be in. Right? So I'm excluding here the regime where your test error is lower than epsilon. Right? If your test error is lower than epsilon, then why are you doing this? You're wasting your time. Right? Just go to your boss, show the results, and you get a promotion. Right? And move your stuff to the window. So in this case, we're always, the test error is always above the epsilon. Right? So there's these two regimes. So either you increase your training data set and you get stuck here. Right? And this is the regime number 1. And this here is regime number 2. Okay. And so without looking at the notes, one of them is high bias and one of them is high variance. Which one is high variance? Which one is high bias? Who can tell me? Maybe actually discuss it with your neighbor for 1 minute. Don't look at the notes. Is it in the notes? Is it very big? Oh, it's very big. All right, okay, never mind. Okay. Giving it away. All right. This here is high variance. This here is high bias. Right? So high variance. High, and here's bias high. And so let us just think about this for a second. Right? So what's happening in these two regimes? Right? So let's first think about this thing here. Right? So here we have the high bias regime. So what's happening? You're training your algorithm, you're using, in both cases, by the way, I assume you use all your training data. Right? So basically you increase your training data and you're stuck here. Right? So this is where you're stuck. Basically, you've used all your training data. Right? You move from the left to the right. Does that make sense? So if you're in this regime here, the important thing is your training error is higher than epsilon. Right? So that's very, very important. Like, your algorithm cannot even achieve the error rate that you want on the training error, on the training data. Right? The data it was allowed to look at. Right? So this means something is wrong. Right? You're somehow modeling the wrong, you have the wrong model for this data set. Right? You have a bias problem. Okay? So in this case, a few things are important. If you're here, more training data will not help you. Can anyone tell me why more training data will not help me in this case? I've seen this many times. People in this scenario, and they go like, our error is still too high. Let's add more training data. It's going to help. Always helps. Right? It doesn't. Why does it not help? Yeah. Right, so adding more training data always decreases your test error. That's good. Right? But it only decreases the test error, like the gap between the test error and the training error. Test error will never be lower than the training error. And the training error will only go up if you add more training data. Right? So the training thing will go up, and the test thing will go down. Right? But it will never move below epsilon. It cannot. Right? Because the training error is above epsilon already, and it will only go up. Okay, so you're shrinking this gap. But this is not your problem. Your problem is not that that gap is too big. Right? That's very, very important. That can save you thousands of dollars if you spend a lot of money on new data and then you realize afterwards it didn't help. Right? Okay, so what you want to do in this case, right? And I guess maybe I don't write them all down. It's like, so how do you detect this regime? So the important thing is that the training error is above epsilon. The training error itself is too bad. And number two, the second giveaway, is that the test error is only a little bit higher than the training error. Right? There's a small gap, and both of them are bad. That's a high bias region. So if you're in that setting, what you need to do is you need to make your model class more complex. So you have to increase the power of the algorithm. Clearly, your algorithm has a hard time understanding basically the shape of the decision boundary on your data set. Right? So for example, because you made a linear assumption, and it's just not a linearly separable data set. So in this case, what you need to do is you have to change your algorithm to be more complex. There's a few ways of doing this. So one thing is kernelization. We will talk about this maybe still today. Add features. Right, so something is not expressive enough. If you add more features, your algorithm may be more expressive. Sorry, where are we? Am I doing out of order? Yeah. And boosting. And boosting is something we will cover again in a few classes. So this, in some sense, you see what we are doing here. So right now I'm telling you how to detect the two regimes. In the next couple of lectures, I will then show you what to do about it. So we will cover boosting, we will cover kernelization, and adding new features is kind of on you. Any questions about high bias? All right, so the other one is high variance. So what is the high variance setting? Again, two giveaways. The training error is below epsilon. Right? So on the training data set, you're doing great. right? If that was the error you wanted. But the problem is the test error is too high. So you have a big gap between training and test error. Right? So what you need to do is shrink that gap. That's basically what happens. So all the remedies here will move up the training error and move down the test error. And if you're a little lucky, then they will basically converge below that epsilon, and then you're done. Okay? If you're unlucky, they will converge above it, and then you're in a high bias regime. Right? Then you have to address the bias. Right? So that means you still have too much bias left. So you're trading off one for the other. So that's the whack-a-mole thing. Right? So if you reduce, the same thing by the way here, if you address the bias, if you do kernelization, you add features, you do boosting, what could happen is that now your training error goes way down, right? The testing error probably also goes down, but there could now be a big gap, and the test error is still above epsilon. That means you now you traded off bias for variance. So now you have to address the variance, right? And so that's in some sense this balance that you have to strike. So in this case, one more time, the training error is below epsilon. That's good, but the testing error is above it. So there's a large gap between the two. So what can you do? One thing for sure is you can add more data. Right? So in the high variance case, adding more data is great. Because adding more data will move training error up and test error down. So that closes the gap. Right? Hopefully below epsilon, then you're done. Another thing is bagging. That's something we will cover very soon. It's pretty cool. And so another thing is you can reduce the complexity. Right? So maybe you're using a model that is too complex and it's hard to get the regularization right. Right? So reduce model complexity. One thing you can do, decrease regularization. Increase regularization. And here, by the way, we have to do decrease regularization. Do I have that here? I just have decrease and increase regularization as in terms of model complexity, I guess, in this case. Okay, any questions about these two settings and what to do? Yes?
If your noise is higher than epsilon, what do you do?
If your noise is higher than epsilon, then you blame the person who collected the data. That's hard, right? So if your noise, does anyone remember what do you do in case your noise is so high? Yeah? You can add more features, right? So that's one option. Noise is a function of the features, right? You can also do data cleaning. So if you do this a couple of times and you're always above epsilon, then at some point you seem to suspect that you're of these bars, right? Of this variance, variance, bias, and noise, right? Maybe that in itself is larger than epsilon, right? So that could of course be, right? So that's too large, then you have to do data cleaning. Right? Also look into are the labels correct, etc. Right? But certainly adding features is a good one. Yes, good question. Yeah?
Is training error means a total error or average error?
It's the same thing. You just divide. It's just divide by the data set.
Like, is it possible, like more data you have, like somehow the training error goes down?
Oh, I see. Yeah. If you compare it with more data, you always have to average. Yeah. But the error is usually a rate, right? So in some sense, the error means if I sample a point randomly, what's the probability of getting that point wrong? That's what an error is, right? If you have more data, the training error will always go up if you don't change your model. Yes, right? Because it's harder. Or it may stay the same if it's totally separate, but it'll never go down. Yes. Yeah, at some point you converge, right? So this graph here converges, right? So at some point it basically doesn't make any difference anymore. But more data will never bring the training error down. That's the important thing to know. Right? And test error is always greater equal the training error. Yeah. One more time, sorry. Yeah, in this case, yeah, just to get this graph consistent, yes. One thing you can do, by the way, is if you do cross-validation, then you could actually get standard deviations, right? And that actually is not a bad thing. To be honest, when I do this graph, I do k-fold cross-validation, and then I actually draw error bounds around here, because that's actually very informative. How much does it actually vary? Yeah. Yeah.
What if you're like, what if the data is actually linearly separable and you're using some algorithm like for decimal, you're getting like random hyperplane, but then adding more data in this case would actually increase the training error?
No. Adding more data would not help you, right? Your training error is still 0. Like if it's a linearly separable data set, and you get it completely right, then you have 0 training error. Adding more data, if it's still linearly separable, it's still 0. And if you're really unlucky, you get some point that now makes the data set not linearly separable anymore, and now you get a larger error. But it's not going down. Yeah. By the way, it's always a little noisy. If I say it can't go down, that's up to the fluctuations that you get. Yeah. Okay, any more questions? So please keep this in mind, right? You will be later on, if you use machine learning algorithms in real life, right? You will be in these scenarios, right? Where you basically, that's in some sense all we ever do, right? If it just works, then you just stop, then you're done. But typically, the reason they hire a data scientist is because it's not easy, right? And so you always have algorithms that don't perform well enough, and your job is it to now improve this algorithm. That's exactly why they hired you, right? So if you now, use a systematic approach, right, you can actually, do much, much, much better than if you just randomly try different things or something. And so what we will do now is actually go through the different settings. So there's a lot of stuff here that I actually wrote down that we haven't covered yet, and that will be the next couple of lectures. So basically attacking very systematically high variance setting and high bias setting. Yes? It's per sample, so you divide by the size of this data set. Is that there? Okay, let's just move on to kernels. Sorry, Sylvia, can I give this to you? Yeah. Actually, let me give you a few over here. All right, and what I want you to do, just to, we start with a little quiz. So here's basically the idea. Imagine you have the following data set. here are my crosses and here are my zeros, so my O's and nods and crosses. And as you can see, basically, these are drawn from some kind of distribution where the O's are basically in some circle, and the crosses are right at the origin, right? There's some small Gaussian distribution here, basically, of crosses, and the circles are around it. And this whole data set is just two-dimensional. So this is an old trick, is basically, and people came up with this a long time ago, is to make classifiers more powerful. One way is just to add more features, right? Does anyone remember in which regime do you want to add more features? High variance or high bias? I heard both of them. High bias, right? High bias. So let's assume we are in a high bias setting. And why is this? Because we use a linear classifier, right? Your cousin, who you usually trust, tells you this data is linearly separable. Don't even look at it. Trust me, right? So you invest in this and you buy a linear SVM. You even pay the patent fee and everything. And now you want to train this. Turns out it does pretty badly, right? So what it would do is basically train something like this, right? So you get roughly 50% error. So you feel like something is wrong. So you look at the data set, and now you've already invested so much in the linear classifier, you don't want to give it up, right? You've already paid the royalties. So what can you do? Right? And an old trick is to basically, in this case, you could, of course, if you know more about the data, try to extract more data, more features. But one thing you can also do is you can take the existing features and try to construct new features out of it. And so basically what you do is you take your vector x and transform it into phi of x, where phi of x is higher dimensional. Can anyone tell me a transformation of just one more feature to add to make this here linearly separable? I'll give you a minute to discuss it with your neighbor. I know some people already see it. Is it? Okay, any suggestions? Yes? Sorry? Oh, polar coordinates. Oh, that's good. I like this one. Yeah, that's right. So I could just take x1, x2 and just change it basically to the, radius, I guess, and what do you need? The angle, I guess, right? The angle. So if you just have the radius and the angle, then that actually works pretty well. It's very nice. I like this a lot. That certainly works. Any other suggestions? Yeah? That's right. You could add another one. You could say x1, x2, and distance from the origin is x1 plus squared x2 squared, right? Square distance, whatever. That's exactly right. And there may be others as well. So, so the crucial point is that if I basically add more features to it, right? So if I take my existing features and just add strange transformations of them, I may make a very easy problem, a very hard problem, easy. Okay? And so instead of actually taking a much more complicated classifier, maybe I just take some, add some features that's cheap, doesn't cost me very much, and now I can use this beautiful linear framework, right? And the nice thing about linear classifiers is We have, for example, SVMs, right? They're very easy to learn. We know exactly what they're doing. So, why not just do this? Any questions about this? Actually, I have a demo here, but the computer is acting up. Guess I have no internet anymore. Yeah?
Why do we keep x1 and x2 inside our vector? Hasn't it already chosen?
Right. So in this case, you don't need don't need x1 and x2 anymore. But typically, the idea is you just add more features that then actually make your problem easier, right? I mean, it seems pretty bold, pretty confident to remove them, and that would really, assume. And this is there's a toy example, right, where you actually happen to know the perfect feature, which is, in polar coordinates, basically the radius, the distance from the origin. Typically, you don't know that. Okay, so this is great, right? So typically, in this case, we know exactly, this is exactly what you're saying. We know exactly which feature to add, because we can just look at the data, and the data actually is trivial. Typically, this is not the case, right? Typically, we have a data set, we have a bias problem, and we want to add more features to make our classifier more expressive. But it turns out, of course, we don't know which features to add, right? It's actually very hard. Right? And so a good thing to do is actually say, well, why don't we just add any possible feature we can think of? Right? That's the grab bag. And so here's the idea. We can take our x1 to xd. And so one transformation we could make is say we take any kind of nonlinear interaction between any two features. So the first thing we just say, just add a bias term 1. Why? Well, why not? And then we have x1 to xd. We just keep our old features. And then we take any two interactions between them. So let's take second order, first order interactions. That's basically x1 squared, right? And then, wait, is that correct? Oh, sorry, x1 times x2. Then x1 times x3, x1 times xd, then x2 times x3, and so on, until you basically get at the end, xd minus 1 times xd. Then you take any three features and multiply them with each other, right? And you do this all the way until the end, until you get x1 times x2 times xd. So that's any d features multiplied together, right? So basically I'm saying there may be some interactions between features that are nonlinear. Right? If we have something, if this feature is large and this feature is small, that actually tells me something, right? If I just have a linear model, that's really, really hard to capture, right? So what I'm doing is I multiply the features with each other. Okay, and this way I get these, for example, here x1 times x2, right? That's suddenly a nonlinear, relation that I can now capture. Can anyone tell me how high dimensional this vector is? I'll give you a minute to work it out. Okay, can anyone tell me? Yeah. It should be 2 to the power d, that's right. So each one of the features can either be in or not in. And so you have a binary decision, so you have 2 to the d, right? There's no internet in this room apparently, but I managed to get it on my cell phone. So I want to show you a little video. So let's see if this works. Okay, awesome. So what you see here is a data set. You see the blue dots in the middle and the red dots around it, right? And so the classification boundary that we would like to have is the circle around the blue points, that separates the blue and the red points. But we have a linear classifier, so we don't know how to do this. But I now show you basically, I just want to visualize to you if we basically now add more features, we just have to add this one feature that basically is the distance from the origin. Now this turns from a 2-dimensional data set into a 3-dimensional data set. Oh yeah, it's the good stuff. And now if we decision boundary now is no longer a line, it's a plane, right? And we can fit the plane exactly to cut off the blue part, right? And if we now go back to the original data set and visualize this decision boundary, right? This is what we get, right? So we get exactly the decision boundary we want. Just with a little link. Thank you. All right, I see you all on Wednesday.